When neural networks scale past the 1 trillion parameter mark, the compute required for inference explodes outward. We are crossing a threshold where raw size collides with the physical limits of commercial hardware. Moonshot AI's Kimi K3, released in July 2026, forces a confrontation with those physical limits. Sized at 2.8 trillion parameters, K3 is positioned directly against proprietary models like GPT-5.5 and Claude Opus 4.8. This specific scale is engineered for highly complex tasks, executing long-horizon coding projects, generating complete front-end user interfaces, and managing multi-step agentic workflows. But running a 2.8 trillion parameter architecture introduces a severe engineering bottleneck. If every parameter activates to process a single token, the resulting compute cost makes the model economically unviable. The second bottleneck lies in memory. K3 targets repository-scale code analysis, requiring a continuous 1 million token context window. Standard attention mechanisms attempting to hold that much context will induce a fatal KV cache memory failure. This block diagram illustrates how K3 resolves these dual bottlenecks. The architecture relies on two parallel tracks: extreme sparse mixture of experts routing to manage capacity, and Kimi Delta Attention to manage context. K3 achieves frontier-level performance through a redesign of how parameters are activated and how memory is allocated, moving away from brute force dense scaling. To understand the compute problem, consider a dense neural network. Activating an unmanageable 2.8 trillion weights for every single data token you input requires a massive expenditure of both electrical energy and processing time. It is mathematically prohibitive for standard inference hardware. K3 addresses this by fragmenting the traditional feed-forward layers. Instead of a dense block, the model relies on an ultra-sparse mixture of experts, or MOE, architecture. This matrix visualizes K3's fragmentation. The network divides into 896 discrete experts. When a token enters, it hits a gating network. This router analyzes it, determining which specific experts are best equipped to process it. The router targets a specific sparsity ratio, selecting and activating only 16 experts per token. In older architectures like Mixtral, models relied on just 8. K3's precision allows for more specific partitioning of knowledge. This sparsity ratio reduces the active compute burden. Over 98% of the model's parameters remain dormant during any given calculation, yet the representational capacity of the model remains. With 896 distinct knowledge pathways available, K3 can draw on highly specialized data structures at a moment's notice. Moving from Python logic to visual data analysis, the model rapidly routes through entirely different combinations of experts. Cautionary. While compute is saved during the forward pass, the memory footprint to hold 2.8 trillion weights on standby demands significant clustered VRAM, and that VRAM requirement compounding when we apply this massive capacity to extreme sequence lengths. The 896 expert MOE provides a mathematically viable path to achieve 3 trillion parameter capability without exceeding the compute thresholds of modern inference clusters. Pushing a model to 2.8 trillion parameters is only half the architecture. K3 relies on a continuous 1 million token context window to process repository-scale code and native video data. This line graph shows the primary obstacle to that scale. Standard self-attention suffers from quadratic scaling. As sequence length increases, memory usage curves sharply upward. Standard attention requires storing a key value cache for every single token to retain previous context. At 1 million tokens, that cache violently overflows available GPU VRAM. To manage this memory requirement, Moonshot AI implemented Kimi Delta Attention, or KDA, paired with Attention Residuals. Notice how the vectors function. KDA alters memory calculation by storing only the deltas, points where information changes. To ensure early tokens aren't lost, Attention Residuals draw a structural link, maintaining long horizon stability to the end of the million-token sequence. Returning to our memory graph, we can see how these two mechanisms combined create a manageable linear progression. This optimized memory footprint directly enables the model's native multimodal support. K3 can ingest thousands of dense visual and video tokens directly alongside heavy codebases. This linear attention method allows the model to analyze massive, unbroken repositories of code rapidly and smoothly, without dropping vital context. Because KDA prevents fragmentation, every variable and function remains accessible across the entire 1 million token span. This structural advantage shows in independent benchmarking, specifically against models that struggle with long context retrieval tasks. Without Kimi Delta Attention, a 1 million token window on a 2.8 trillion parameter model is physically impossible to run. KDA supplies the mathematical efficiency required for the model's enterprise use cases. Transitioning from theoretical architecture to practical deployment reveals how these structural choices perform in the real world. This ranking dashboard places K3 in the number 4 overall spot, securing a 57.1 score on the Artificial Analysis Intelligence Index. It sits alongside Claude Opus 4.8 and GPT 5.5, while topping the front-end code arena. It trails Claude Fable 5 and GPT 5.6 Sol on some general metrics, but its specialization in coding is its primary strength in the open weight tier. That performance relies on a structural trade-off in K3's inference pipeline, the implementation of always-on max reasoning. This flowchart demonstrates what always-on max reasoning means. Every query forces the model into maximum compute loops, analyzing logic repeatedly before it is allowed to generate an output. For many tasks, this results in higher latency and responses that are often overly verbose. Developers have also reported higher hallucination rates in specific non-coding edge cases, as the forced reasoning loops overcomplicate simple queries. This heavy compute burden is reflected in the official API pricing, $3 per million input tokens and $15 per million output tokens. To mitigate this cost for developers analyzing large codebases, Moonshot offers a 30-cent cached input price. K3 functions as a slow-thinking developer tool, prioritizing deep logic execution over the low-latency response times typical of consumer chatbots. When we unify these elements, we see how the 896 expert MOE and Kimi Delta Attention function as a single system. Capacity and context optimization are structurally dependent on one another. This combination pushes Chinese open-weight models into the frontier tier of artificial intelligence. The historical significance of this architecture culminates on July 27, 2026, with the expected release of K3's full model weights. This marks the first time a 3 trillion class frontier model has gone fully open weight, bringing proprietary-level scale to the public domain. Open source development is no longer just catching up. By opening K3, the open weight tier is matching proprietary labs in scale and architecture. For machine learning engineers, the challenge has moved from model scarcity to the complexities of local inference engineering and cluster optimization. Kimi K3 signals the end of the era of lightweight Chinese models. The open weight ecosystem now possesses massive, locally deployable frontier intelligence.